Hello everyone, and today I'd like to present the review of our competition, which was held in the context of the AINL conference this year. And the task was on detection on AI-generated scientific abstracts in Russian this year. I'm going to tell you about our motivation and task description of the evaluation. Also, I'll tell you about the data set and baselines and results, and then the participants will tell us about their solutions in this competition. So, first of all, I'd like to thank our team. So it is Tatiana Batura, Valentin Malych, Milana Schwenk, and me who supports and helps to create this competition. So let's start from motivation. And I think all you know that in recent years, developing large language models has revolutionized NLP and many other domains. And then nowadays, generated texts are really close to human written, to human level writing, and makes it increasingly challenging to differentiate between automatically generated text and human-generated content. And it's really impressive. I think it's undoubtable. But however, there are some domains in our life where this usage is not desirable, such as fake news generation or writing scientific papers, and we should stop it from usage. And so yesterday, in the context of panel discussion and after it, we discussed how it is important to detect such texts and how it is important to support our community with different kinds of evaluations. So this year we aim to detect AI-generated abstracts for scientific papers in the Russian language to facilitate research and development tools for this particular language. So probably, as you know, there are a lot of tools and works are developed for English, and quite less are done for Russian language. So we think it is important to develop and support these efforts. And what about task description? We tried to create interesting task description, not only differentiate between human written and AI generated, but to involve some more challenging. So the task was as follows. So we have a train set which includes text with 4 labels. So a part of text was initially human written, and the other texts were generated by 3 models, either GPT-4, GMA2, or Llama 3. In stage of development, so dev set includes the text with 4 labels and one more, which was the text which were generated by the unknown model. And I don't know if participants guessed what was the model. It was GigaChat Lite. So in the stage of development, their participants should implement the multi-class classification. And during the test set, the text includes another unknown model. It was different from DevSet, and it was text generated by DeepSeek. So here, okay. In test, the texts were generated by 4 different models, and also includes some of them which were written by human. To construct data set, we automatically collected human written samples, and each samples includes domain, title, abstract, and keywords. And then we prompted their aforementioned models to generate abstracts with the given domain, title, and keywords. So thus we construct the data set. And also we applied some post-processing to the generated text. So obviously we removed empty and insignificant outputs when the models refuse to generate some output. And also we removed model-specific text beginnings while preserving the main content of the abstract as is, because we noticed that some models tend to start text with some patterns, and it would be very easy to classify if we keep them. Also, what about domains in our data set? We choose 10 domains for train and dev set, and they were exactly the same for these two sets. And for test set, we include 2 new domains, economics and biology, which were absent in train and dev set and weren't seen by the solutions of by the systems which our participants developed. Thus, we invited participants to propose solutions to the following key challenges: handling data that extend beyond the training set, so generalization to new domains like we previously noticed, like biology and economics, and also detecting text generated by a model not included in the training data. So it is about generalization to new models. So it is interesting if different models keep some artifacts that can help to recognize the text is written by the particular models. So a little bit of statistics of our competition. So we got about 200 submissions for all the competition. 2 participants took part in dev stage, and 5 participants took part in test stage. And I think for the first time, it's quite a nice result for us as organizers. Also, we provide 2 baselines. We prepare 2 models. One is logistic regression with TF-ADF features, and another one fine-tuned BERT. And label unknown model was chosen by the threshold. Just a simple approach. And what about results on a test set? Our baseline here was logistic regression with this score, and the third place was for this team who beat the baseline. The second is for team of Konstantin. He will present his solution. And the first place is for this team who beat the baseline the most. So now I'd like to invite the participants to share their solutions. And our first participant should be Konstantin.
Hello everyone, my name is Konstantin Zaitsev, and I'm going to present my results on the shared task. And as it said before, the shared task is dedicated to the detection of AI-generated text, and the texts were produced by human and other language models, and dataset contains Russian scientific abstracts from various domains. So our research objectives for this shared task were as follows. Firstly, we conducted experiments with the various neural network models our motivation behind this is to determine whether determine the best model for this task. Secondly, we integrated statistical features with neural network models. We did it because on the leaderboard, TF-IDF baseline shows superior performance comparing to the BERT model. And finally, we conducted experiments to establish an optimal threshold for identifying text generated by unknown model. So our first approach was to simply fine-tuning decoder models. We used decoder models because in the other studies this architecture shows better performance on the detection of generated text compared to the encoders. So our architecture was quite simple. We firstly utilized the last hidden state from the decoder and then pass it through the linear classification layer. Here on the slide, you can see our evaluated models. We selected these models because for some reason. The first reason is that all models had in pre-training dataset Russian language, so these models should work good enough for detection Russian scientific text. Especially Yandex GPT was um, pre-trained on Russian text, and we hypothesized that this model uh, would would have better accuracy than the other models. So the second reason is that the second reason for choosing the Gemma is that they have great potential for the further experimentation with other methods such as sparse autoencoders and I, yeah, we fine-tuned decoder models using LoRa adapter, and here you can see our results on development set. We used this threshold because this threshold shows the highest accuracy on our experiments on development set. And here you can see that Yandex GPT achieved the highest accuracy among the other models. And surprisingly, Gemma with 2 billion parameters achieved a slightly better performance than the Gemma with 90 billion parameters. So the second approach was about the combination of TF-IDF and the neural network model. And our motivation behind this combination is that, as I said before, the TF-IDF baseline was better than the BERT model on the leaderboard. And therefore, we hypothesized that the statistical features with neural model could improve detection and accuracy. And here you can see our architecture. We firstly fed text into the TF-IDF and Gemma modules, produced outputs from these modules. We pass through linear layers, and outputs from linear layers we summed and fed into the classifier. And as a result of this architecture, we get labels probabilities. So it is important to note that we uh, do not fine-tune Gemma module, decoder model, and we fine-tune only classification, linear layers, and classifier. And the results for this approach will be presented on the overall results section. And final approach was related to the perplexity. Uh, perplexity analysis is a commonly approach for detection generated text. And there is assumption that human written texts usually have higher perplexity than machine generated ones. And the explanation behind this is that humans are more likely to write texts that are not typical for language models. So here you can see commonly used metrics for the this task, usage of perplexity. It is log likelihood, rank, entropy, binoculars. And binoculars, it is a recently developed method. And so here, and we can say that metrics alone often show limited effectiveness. It means that if we use them without any strong baseline, we could get lower accuracy. So our goal in this approach was to improve model with text features by adding perplexity features. So for feature extraction, we used Gemma and Llama for computing metrics. We selected these models because the text in the dataset were produced by these models, but with larger sizes. So our hypothesis for this is that text generated by these models should have lower perplexity, and therefore it should improve classification. And as a learning algorithm, we used gradient boosting implemented in CatBoost. So here you can see results on the development set, and for each feature combination, we found out the optimal threshold that achieves the best accuracy. And also here B means binocular features for Gemma and Llama. And it is important to note that rank, entropy, and so on, we calculated only for Gemma. And as you can see, the highest accuracy was achieved by combination of binocular feature of Gemma and rank. And also the second place is combination of binocular features for Gemma and Llama. And according to our experiments, we selected the best approaches, models, and feature combinations. And here you can see our final results on test set. So we choose Yandex.GPT, Gemma, combination of neural network model with TF-IDF, and combination of text features used in CatBoost, and binocular features for Gemma and Llama. And here the best accuracy was achieved by a combination of binocular features of Gemma and Llama, and the neural network shows worse performance comparing to this combination, and it can be concluded that the combination of binocular features or other features related to the perplexity could be a great baseline for the text detection AI-generated detection task. Thank you for your attention.
Thank you, Konstantin. Are there any questions to speaker?
Thank you for your speech. Could you explain Why did Gemma with less parameters perform better?
Frankly speaking, I don't have answer for this, but maybe it the result of different training settings, because Gemma with 9 billion parameters was trained in, as I remember for one batch size, and Gemma had larger batch size.
Okay, thanks.
Thank you. Any other questions?
Thank you for your talk. Can you please repeat? I guess I missed it. Why haven't you used any encoder models? There are lots of them for Russian, like Roberto for Russian or so on. Why you use decoder models in the last language?
Yeah. On the other studies, we noted that approaches based on the decoder models shows better performance than the encoders, and also we conducted experiments with encoders like Roberta and other encoders that supports Russian, and they often show worse performance than the decoders.
So the insight here is that for this task, decoders are better feature presenters like this. Yeah. Thanks.
Hello. It's interesting that TF-IDF plus logreg is a good baseline. Did you explore features that we can extract from TF-IDF or not?
No, I didn't explore this, but the interesting way to maybe find out the better solution that just use TF-IDF.
Okay, thank you.
I guess we have to move on, and we'll invite Alexandra to present her solution.
So hello, everyone. My team and I are so honored to participate in such motivating and challenging competition. And we would like to say thank you to everyone who took part in assembling it. Now I'm excited to walk you through our solution review for the AINL shared task on authorship attribution, a challenge focused on distinguishing between human-written and AI-generated texts. And this was a collaborative effort by our layer team at Salute Devices. So let's go into the task definition. At its core, the task had two main goals. First, to determine whether a given piece of text was written by a human or generated by an AI model. And second, if we identified it as AI generated, to figure out which model did it, a model known during training or completely unseen. The second part really pushes the boundaries into what's called out-of-distribution detection. And to address these questions, the authors of competition built a comprehensive dataset. They used 5 models, including some of the most powerful publicly available ones, GPT-4 Turbo, Llama 3, and Gamma, as well as 2 undisclosed models for robustness. They prompted them using real academic paper titles and keywords, and then they filtered out noise, such as incomplete outputs or obvious model-specific signatures, to ensure clean and challenging samples. So the training set spanned 10 domains, totaling about 35,000 texts. For testing, the data is split into public and private sets. The public test set included an unseen model, while the private set expanded further, adding new domains and other models never encountered during training. And that gave us a tough but realistic environment for evaluation. Before training, we performed standard cleanup, removing emojis, strange Unicode characters, and formatting noise. But more importantly, we incorporated smart augmentation strategies. For instance, we varied text length dynamically during training, which helped the model generalize across both short and long passages. And our core model was a large language model based on Mistral 7B. which offered an excellent balance of performance and open access flexibility. We designed it with two classifier heads. One performs binary classification, deciding whether the text is human or AI written, and the second is a multi-class head that tries to pinpoint which AI model produced the text. So a key adaptation we made was appending a special CLS token to the end of each input, and here you can see like a short schema of our solution. And the model token uses the final hidden state of this token as a representation for classification. Then each head uses two simple linear layers, keeping it efficient but effective. Okay, so next is our training strategy. And for training, we leverage LoRa, a parameter-efficient fine-tuning approach that let us update only a small subset of weights while keeping the base model mostly frozen, and that drastically reduced training costs without sacrificing performance. We also address class imbalance using weighted loss functions, and we explored two training paradigms. A one versus all setup for better specialization and a standard multi-class approach for holistic learning. I'd like to note that all versus all approach showed the best results. So in the final model, we used all versus all approach, even though we conducted extensive experiments with both. So let's go into the hyperparameters. We used, just to quickly highlight the technical configuration, we trained with 512 token sequences, a batch size of 128 with gradient accumulation, and use brain float 16 precision for efficient compute. And for LoRa, we tuned it with a rank of 8 and a dropout of 0.1. So we did a one epoch warm-up and set the standard learning rate for training. Yes, here you can see the LoRa configuration. So let's go into the results. Well, as you can see, our model achieved a strong performance, and on the dev set, which included unseen models, we hit over 91% accuracy. On the harder private test set, which also introduced new domains and unfamiliar models, we still maintained over 86% accuracy. And this speaks for robustness of our method, especially injecting out of distribution content. So do you want to learn more? To build on this foundation, we also developed a framework called GigaCheck. It doesn't just classify whole text, it can detect AI-generated intervals within larger text. So if only a part of a document is AI-written, GigaCheck can spot it. You can explore all the details in our paper, co-authored by our team, when we unpack the architecture and the detection mechanism in more depth. A little spoiler alert, we use detection transformers, where we apply the approach from CV into NLP. And you can try it yourself using our free Telegram bot if you're curious to test our system. But it's free to use, so they're currently available only in Russian. It's powered by the same model and trained on our custom data set. And if you'd like to stay in the loop on what our team is working on, from cutting-edge deep learning projects to practical tools and the occasional meme, feel free to join our Telegram channel. And I'd like to say thank you. This wraps up my presentation. Thank you again for your time and attention. And I'm happy to take any questions or dive deeper into any part you're curious about.
Alexandra, thank you a lot. Are there any questions?
Sorry, can you please show your Telegram bot QR code once again? I wasn't able to scan it.
Okay, this one, I guess.
Well, thank you for your presentation. I have a question about your system of detecting the parts of the text generated by AI. Is it sentence level or how, and is it open source?
Honestly, it is kind of unique because like a lot of open works, they use sentence levels or even paragraph levels of granularity for detection, but our approach uses a really precise one. We detect based on characters. So if you have like a text and there are parts of AI written segments in there, our approach will highlight the precise, we'll try to highlight the precise span, the precise interval based in characters where the AI wrote it.
Thank you.
Thank you. Are there any questions?
Thank you for your speech. You said that your model had two heads, one for human or AI, and the second for particular model. And how did final result was calculated?
Yeah. So
okay.
Sorry. So if to say it really concise, we use only the second head to predict the precise model that generated the text, and we use a threshold that we chose based on the development set metrics. That threshold for us was 100% level of confidence. And if the confidence of the model is less than 100%, then we mark it as unknown model. And the reason we used two heads was for integrating multitask learning in our task, which boosted the metrics empirically, of course.
Thank you.
Thank you. Any questions?
I have a question, if I might. Thank you for the presentation. It was really nice to see. You mentioned that you have the approach from CV, which you apply for NLP. Could you give more details on that?
Yeah, thank you for this great question. Honestly, let me show you. Here at the end of the slide, you can see the name of our paper. There it is described in more detail than I'm going to tell you now. But shortly, to just give you the intuition, we extract the features. Like we have classic CV detection approach named DETR. It is a detection transformer, which is like a soda in the field, and we applied it into NLP setting. So it's like detecting some objects, but in 1D space. So in an image, you have a 2D space, basically, and text is 1D, and we just perform a 1D detection. So for features for DETR, we use features extracted from our base model, which is usually Mistral 7B. So we use its hidden states as features to pass to the DETR.
Thank you. Thank you. I'll read the paper, of course. Thank you.
Thank you.
Thank you a lot. Any questions? So just for me, it is interesting if our competition was on time for your research. So what was the first year research? And you tested in our data or vice versa?
If I correctly understand the question, we released our paper at the end of the last year, at the end of the 2024. But honestly, at that setting, we only have a setting of classifying into 3 different classes, like AI, human, or mixed. And then we have a setting for detecting the exact intervals within the text that were generated by the AI. And for this competition, we had to add a separate additional head for classifying the exact model. So that was a bit challenging because we couldn't apply our ready-to-use framework. So we had to develop it further for the competition.
Okay, I see. Thank you a lot. If there is no any questions, Thank you, Alexandra, and thank you, Konstantin,
Thank you.
for your reports.
Thank you, everyone.
Okay, and if you want to try your own solutions or your own ideas to solve this task, it is still open in Codalab, and we open data set in GitHub, so you may send efforts, and you may use the data for your own tasks and problems. So thank you a lot for your attention and for attending. If you have any questions about the competition itself, you may ask them, or if you have any other questions.
Okay, thank you for your presentation. I have a question regarding unknown label. Why have you chosen only one model for unknown label? So, because the point of, as far as I understand, the point of unknown label is like we need to. This data can be from like any model. Like, why stick to the one?
I see. Thank you for your question. We were limited by the time and by the resources,
Okay.
but yeah, I agree that it would be really interesting how well the texts can be clusterized, for example. Maybe it will be our future experiment. Thank you.
Thank you for the answer.
Thank you. It was interesting to see this competition. And do you think this problem is solved, this task is solved? How hard would be for me to make AI generated abstract and to make all my article using AI and to be not suspected?
This question regarding to the quality of the models or to the quality of the tools which distinguish between human written and auto-generated text? What is the most important in your question? Are there any models which may produce the text which are really close to human?
Yes.
Hard question. I think it depends on a lot of aspects like prompt engineering and so on. But regarding to the results, there is a field for improvements for this task. And your concrete text may be and classified, both classified and unclassified. So, but I can say that this task is solved, so there is an area of improvement still.
Thank you.
Thank you for this competition. Really interesting to hear the results. I'm interested, probably I've missed it. What was the model that was hardest to notice that is generated? What is the model among models you presented were most close to the human, and the most errors were made by the participants?
Yeah, I see. Thank you for the question. I don't have this information right now, but as I remember, the most close to human written was GIMA2 by our analysis, and other were more simply detected.
Thanks.
Thank you.